Okay, so if you've ever written any Python, I bet you've hit this wall. You change one variable, and all of a sudden, a completely different variable that you didn't even touch also changes. It's a classic, head-scratching bug that trips up literally everyone. So today, let's finally pull back the curtain and understand what is really going on under the hood.
So here's our game plan. First, we're going to tackle the variable illusion that causes all this confusion. Then we'll reveal the correct mental model, labels versus boxes. After that, we'll break down the two critical types of objects, immutable and mutable. We'll walk through the most common pitfalls they cause, and then we'll connect the dots to why this is so crucial for data structures and algorithms. We'll wrap it all up with a mastery checklist to make sure this stuff sticks. All right, first things first, let's look at the exact problem, the piece of code that causes so much confusion and has such a surprising result. So here's the puzzle. You've got a list, A, which is 1, 2, 3. Simple enough, right? Then you make a new variable, B, and you just say B equals A. Now you only modify B. You run b.append 4. So what do you think A is now? The shocking answer is that A is also 1, 2, 3, 4. Wait, what? How is that even possible? We never touched A.
And the reason this feels like some kind of weird black magic is because our intuition is just wrong. We instinctively think of variables as little boxes or containers that hold our data. And if A and B were two separate boxes, then yeah, changing one couldn't possibly affect the other. But that's not how Python sees the world at all.
All right, so it is time to completely tear down that old mental model and build the right one from the ground up. This next idea is the absolute key to understanding how Python's memory and variables actually work. And here it is. This is the single most important idea you need to get. Variables in Python are not containers. They are labels. Think of them like name tags you stick onto an object. They don't hold the data, they just point to the data, which is an object living somewhere in memory. And this slide just lays it out perfectly, right? On the left, you've got that old wrong box model, with the number 10 literally stuffed inside the variable A. But on the right, that's the Python reality. The object 10 exists on its own, and the variable A is just a name tag, a label with an arrow pointing to it. This distinction changes everything. And just a quick technical point here, because this is important. Unlike other languages you might know, like Java or C++, Python doesn't really have primitive types. In Python, everything is an object. A number is an object, a string is an object, a list is an object, and variables are just references or labels pointing to these objects. But for learning, it's way, way easier to think about them in two main groups based on how they behave.
Okay, so once you accept this label model, you'll see it leads to two totally different behaviors depending on the kind of object a label is pointing to. And this is where we get to the super important concepts of immutable and mutable objects.
So we can basically split Python's objects into two useful camps. On one side, we have what we'll call primitive-like objects. These are things like integers, floats, strings, and tuples. The key thing about them is that they are immutable. That's a fancy word for unchangeable. Once you create them, they can never, ever be changed. On the other side, we have our reference-type objects, like lists, dictionaries, and sets. These guys are mutable, which means you can change them in place whenever you want.
Let's see this immutable rule in action. So we start with A equals 10. Then we say B equals A. Okay, so right now, both labels, A and B, are pointing to the exact same 10 object in memory. But watch what happens when we run B plus equals 5. Because the integer 10 is immutable, it can't be changed, Python can't just turn it into a 15. Instead, it creates a brand new object, 15, somewhere else in memory, and just moves the B label to point to this new object. The A label? It's still right where it was, pointing at the original 10. And now for the mutable rule, which, by the way, it's going to solve our original mystery. We have A equals 1, 2, 3, and then B equals A. Just like before, both labels are pointing to the exact same list object. So when we call b.append 4, we are not making a new list. We are modifying that single shared list object directly in place. And since both A and B are still pointing to that one object, of course they both see the change. That's the power and the danger of a shared mutable object. And hey, don't just take my word for it. Python gives us a tool to prove this. It's the built-in ID function, which gives you the unique memory address for any object. So if we create list A, then set B equal to A, you can see that their IDs are identical. It's proof they are just two different names for the exact same object. But if we create a totally new list C that just happens to have the same values, its ID is different.
It's a completely separate object in a different spot in memory.
Okay, now that we have the right model in our heads, labels pointing to objects, let's look at how getting this wrong leads to some of the most common, hair-pulling bugs that Python developers run into, especially when they're learning data structures.
This is mistake number one, the big one, the one we started with. It's assuming that the equals sign makes a copy of the data. Let me be clear, it never does. The line B equals A only ever copies the label, the reference. It never copies the object that the label is pointing to. So when that object is mutable, like a list, you get these spooky side effects. So what's the fix then? How do we get around this? Well, you have to be super explicit. If you want a brand new, separate list, you have to actually ask for one. You can use the .copy method, you can use the list constructor, or you can use a full slice like a //. All three of these tell Python, hey, I don't want another label, I want a whole new object.
All right, the next two mistakes, they're even sneakier, even more dangerous, because they pop up when you start using functions, and they can cause bugs that are an absolute nightmare to track down.
On the left, you've got function side effects. When you pass a list into a function, you're not passing a copy, you're passing the reference, the label. So if the function modifies that list, the change happens to the original object and is visible everywhere. And on the right, oh man, this is a classic pitfall, using a mutable type like a list as a default argument. That default list object gets created only once when the function is defined, and it's shared and modified across every single call to that function forever. Very weird behavior if you're not expecting it.
Okay, so let's tie all of this directly into data structures and algorithms. Because trust me, this isn't just some weird Python trivia. It is absolutely fundamental for writing algorithms that actually work correctly. Just look at this side by side. You pass an immutable integer into a function. Any changes inside just create new objects and repoint local labels. The original variable outside is totally safe. But you pass in a mutable list, and now that function has a direct line, a backstage pass to your original object. Any in-place changes like append or pop permanently change that one shared object. Understanding this is the key to managing state in things like recursion, backtracking, and graph algorithms.
You know what? Here's a fantastic analogy to make this stick forever. Think of immutable objects as sticky notes. You can't really edit a sticky note, right? To make a change, you just have to crumble it up and grab a whole new note. But mutable objects are like a whiteboard. Anyone with a marker can walk up and change what's on it, and everyone else looking at that same whiteboard will see the update immediately.
All right, we've covered a ton of ground. Let's wrap this up with a final checklist to make sure all these ideas are locked in and you're ready to use them in your next coding session or, more importantly, your next technical interview. You need to burn this table into your brain. Seriously, I call it interview gold for a reason, because these are the exact trade-offs interviewers want to hear about. Can you change the object in place? Only if it's mutable. Is it safe to pass into a recursive function without making copies? Only if it's immutable. Can it cause shared side effects? You guessed it, only if it's mutable. Knowing this cold is non-negotiable. So look, if you only remember one thing from this entire explainer, please let it be this sentence. If the object is mutable, changing it inside a function changes it everywhere. Internalize that rule, tattoo it on your brain. It will save you countless hours of debugging, I promise. Now go look at your own code. I guarantee you'll start seeing this concept in action everywhere.